Chapter 6, Module 2. In this module, we shall discuss two very important results. The first one is to prove that the fundamental group of a topological space is isomorphic to the fundamental group of any of its deformation retract. And the second one is to show that the fundamental group of any contractable space is trivial. We shall see subsequently that these two results are very important. We recapitulate a few important facts. To each topological space X and a point x0 of the space X, one can associate a group pi1 xx0, which we call fundamental group based at x0. If X is path connected, then its fundamental group is independent of its base point. That is, whenever we take 2 points x0 and x1 from capital X, then the fundamental group of X based at x0 is isomorphic to the fundamental group of X based at x1. Each continuous function f between the pointed topological spaces x x0 and y y0 induces a group homomorphism f sharp between the corresponding fundamental groups. This f sharp has the functorial properties. That is, if I is the identity function from x to x, which takes x0 to x0, then I sharp, the induced homomorphism from pi1x to pi1x, is once again the identity homomorphism. If I is the identity function from a topological space X to X, then the induced homomorphism I sharp between the corresponding fundamental groups is the identity homomorphism. If f is a continuous function from x to y, which takes x0 to y0, and g is a continuous function from y to z, which takes y0 to z0, then g composed f sharp is equal to g sharp composed f sharp. The power of functorial properties can be noted in the following theorem. Suppose x and y are two path connected homeomorphic topological spaces, then the corresponding fundamental groups pi1x and pi1y are isomorphic. So, how do we prove it? Suppose f is the continuous function from x to y, which is given that it is a homeomorphism. Since x and y are path connected, their fundamental groups are independent of the choice of the base points. So, choose any x0 from capital X such that y0 is fx0. We shall show that pi1 xx0 is isomorphic to pi1 y0. Since f is a homeomorphism, f inverse exists and it is continuous. Then the derived homomorphisms, that is f sharp and f sharp inverse, are actually the inverse of each other. How do we get it? That f inverse composed f sharp is identity sharp, but f inverse composed f sharp means it is f inverse sharp composed f sharp, which is identity on the fundamental group. And similarly, f composed f inverse sharp is equal to identity sharp, which implies f sharp composed f inverse sharp is equal to identity on the fundamental group on Y. Hence, f sharp becomes a group isomorphism as desired. Now, we prove another theorem that suppose f and g are two continuous functions between two pointed topological spaces such that F is path homotopic to G based at x0. Then F sharp and G sharp are actually the same map. Suppose I take any element from the fundamental group pi 1 x x0, let us call it class alpha. Then if path homotopic to G implies F composed alpha is path homotopic to G composed alpha, and therefore F composed alpha class is equal to G composed alpha class, so that F sharp alpha is equal to G sharp alpha. Now, the point class alpha is arbitrarily chosen, and therefore we have F sharp is equal to G sharp. Now, if F is a homotopy equivalence between pointed spaces, then the corresponding induced homomorphism F sharp is an isomorphism. By definition of homotopy equivalence, for the function f from x to y, there exists a function g from y to x such that G composed f is path homotopic to identity on x, and f composed G is path homotopic to identity on y. Then G composed f sharp is equal to identity sharp, and F composed G sharp is also equal to the identity sharp. Using functorial properties, we then have that G sharp composed F sharp is equal to identity on the fundamental group of x, and F sharp composed G sharp is equal to the identity on the fundamental group of y. So, this proves that G sharp and F sharp, they are inverse of each other, thereby proving that F sharp is an isomorphism. Now, from this theorem we get a corollary that if A is a deformation retract of capital X, a topological space, and if we choose a point A from the deformation retract capital A, then the fundamental group pi 1 A is isomorphic to the fundamental group of x A. By definition of a deformation retract, the inclusion map I from A to X is a homotopy equivalence. So, as we have proved in the theorem, the corresponding induced homomorphism I sharp is an isomorphism. So, the fundamental group of a topological space X can be obtained from the fundamental group of any of its deformation retract. The implication of the last corollary is really very powerful, because if we know a deformation retract of a given topological space and know the fundamental group of the deformation retract, then we know the fundamental group of the original space. Not only that, if two deformation retracts of the same space is given, then the fundamental group of the two deformation retracts must be same. In the next part of this module, we are going to discuss what will be the fundamental group of a contractable space. Suppose f and g are two continuous functions such that fx0 is y0 and gx0 is y1. That is, a point x0 of capital X is mapped to two different points of capital Y via the maps f and g. If f is homotopic to g, then the theorem says that there exists a path eta in Y connecting y0 and y1 determined by the homotopy such that the following diagram commutes. Now, what do I mean by the diagram commutes that if F sharp is the induced homomorphism from F and G sharp is the induced homomorphism from G, then via the map, the homotopy between F and G, we can construct a function from pi 1 y0 to pi 1 y1 such that if we call that function eta cap, then eta cap composed F sharp is G sharp. Now, how do I define eta cap? Eta cap of any element class beta is defined as class of eta inverse star beta star eta. Now, suppose the homotopy between F and G is H. Then it is a continuous function from x cross I to y such that Hx0 is Fx and Hx1 is Gx. So, now we define eta by that homotopy, means eta of t is equal to Hx0 t. Then eta is certainly a continuous function such that eta 0 is y0 and eta 1 is y1. So, eta is actually a path connecting y0 and y1, and this path is determined by the homotopy H. Our claim is that eta cap, the way it is defined earlier, composed with F sharp is equal to G sharp. So, to prove that, we need to show that the class eta inverse star F composed alpha star eta is equal to the class G composed alpha whenever we pick an element class alpha from pi 1 xx0. That means, to show that eta inverse star F composed alpha star eta is path homotopic to G composed alpha. So, we prove this result in two steps. First of all, in the first step, define a continuous function g from I cross I to y by gst is equal to h alpha s t for all s and t from the closed interval I. Then, for each st belonging to the closed interval I, gs0 comes out to be equal to f composed alpha of s and gs1 is equal to g composed alpha of s. Also, g0t is h alpha 0 t, which is h x0 t, and that is equal to eta t, and g1t is equal to h alpha 1 t, and that is equal to h x0 t, and it is eta t. In the step 2, we utilize this map G and define a map capital F from I cross I to y as follows. If st is defined in terms of eta inverse capital G and eta in the intervals 0 to 1 minus t by 2, 1 minus t by 2 and t plus 3 by 4 and t plus 3 by 4 and 1 respectively. Applying pasting lemma, it is not hard to see that this function capital F is continuous. Also, if we put t equal to 0, then Fs0 becomes eta inverse star F composed alpha star eta. Fs1 becomes G composed alpha, and Fs0t is equal to F1t is equal to Gx0. Hence, this function capital F is path homotopy between eta inverse star F composed alpha star eta and G composed alpha as desired. Now, from this theorem we get a corollary that if f is a function from x to y which is homotopic to a constant function c from x to y, and if I take any point x0 from capital X, then the induced homomorphism f sharp between the fundamental groups pi 1 x x0 and pi 1 y f x0 is the 0 map. So, for that, if we choose any point from pi 1 x x0, let us call it class alpha, then we need to show that f sharp operated on this class alpha will give me the trivial element, that means class C f x0. C is a constant function described by all the points of capital X are mapped to y0. So, we have two functions, one is the function f from x to y and the other function is c from x to y. So, applying the theorem we get the following commutative diagram, that is eta cap composed f sharp is equal to c sharp. Here c sharp operated on alpha is C composed alpha, which comes out to be equal to Cy0, and eta cap composed F sharp is equal to C sharp implies that the class eta inverse star F composed alpha star eta is equal to the class Cy0. So, F composed alpha is path homotopic to eta star Cy0 star eta inverse, which is path homotopic to C of Fx0. Hence, F sharp operated on class alpha is equal to the class C Fx0. Now, we get another corollary from the theorem, which is the very important one. It says that the fundamental group of a contractable space is trivial. Suppose we take capital X as a contractable space and we choose a point x0 from capital X. As every contractable space is path connected, it is enough to show that the fundamental group of X based at x0 is equal to a trivial group. Since X is contractible, the identity map I is homotopic to the constant map Cx0, which we denote by C here by the homotopy capital H. Then, using the previous theorem, we get the following diagram commutative, that is eta cap composed I sharp is equal to C sharp, where eta cap is described as in the theorem and it is induced from the path eta, which depends on the homotopy capital H. By commutativity of the diagram, we get that C sharp is equal to eta cap composed I sharp, and therefore C sharp operated at any member class alpha is equal to eta cap composed I sharp operated on any element class alpha, which in turn gives that the class Cx0 is equal to eta inverse star alpha star eta this class. Consequently, Cx0 is path homotopic to eta inverse star alpha star eta. That is, eta inverse star Cx0 star eta is homotopic to alpha, and hence Cx0 is path homotopic to alpha. So, by arbitrariness of the element class alpha, we have the fundamental group of X based at x0 is trivial. In view of this corollary, we have that the fundamental group of Rn for any n greater than 0 is a trivial group. Now, let us take the identity function I from Rn to Rn and take the constant function C0 from Rn to Rn, which maps all the points of X to the point 0. Then we define capital H from Rn cross I to Rn by Hxt is equal to Tx for all x belonging to Rn and t belonging to I, and this is indeed a homotopy, and this when t equal to 0 we get back the constant function C0, and when t equal to 1 we get back the identity function I. So, it is a homotopy between I and C0, and therefore Rn is contractible. And since Rn is contractible and we know that it is path connected, we can conclude from the theorem, or rather the corollary, that the fundamental group of Rn is trivial. So, we have seen that the fundamental group of a contractible space is trivial. So, the question is, if the fundamental group of a space is trivial, then does it imply that the space is a contractible space? The answer to this question is certainly no, because if we take a 2-point discrete space, say the space is x0, x1, then it is definitely not path connected and therefore not contractible. But loop based at any point, say x0, is only the trivial loop, the constant loop. So, the fundamental group of this space is trivial.